Greetings. If you're watching this, it means you have been chosen to work on this urgent project. Recently, the Caribbean has been ravaged by hurricanes, destroying acres of banana tree farms that are owned by the Cavendish Distilling Company. Yes, the same one that makes the famous banana liquor. You have been assigned the task of synthesizing synthetic banana oil, something that they could use to replace the lost bananas in their drink. As you know, esters are commonly used as flavorings in a variety of foods. Knowing this, isopentyl acetate would likely be the best choice for your synthetic banana oil due to its tasty properties. Keeping cost in mind, this product should be synthesized using isopentyl alcohol and acetic acid, two cheap reagents, via the trans-esterification process. Because of this, we need a lot of the product. You should also apply Le Chatelier's principle and use excess acetic acid in order to push the reaction towards the product side. With that, I wish you good luck and a high yield. To start, we gathered our materials. We used 16.52 milliliters of isopentyl alcohol with 17 milliliters of acetic acid in order to catalyze the reaction. We included 1 milliliter of sulfuric acid along with some boiling chips. This was combined into a 50 milliliter round bottom flask in order to perform under reflux as shown on screen. On the bottom, water flowed into the condenser. On the top, water flowed out. Be sure to first fasten your condenser to the ring stand above, in order to avoid mistakes as you see on screen here. Sure that every tube is securely fastened and that the water is turned on gently in order to ensure that the tube does not pop off. Once the boiling began, we heated under reflux for 1 hour.
Boil.
Once finished, and the product had cooled, we moved the product to a separatory funnel, leaving the boiling chips behind in the round bottom flask. Here, we washed with 50 milliliters of water and drained the aqueous layer. Be sure to vent frequently. Pressure builds quickly and the funnel can explode if one isn't careful. If you listen closely, you can hear some of the air exiting the separatory funnel now. We then proceeded to wash 2 more times with 5% sodium bicarbonate, repeating the same process.
Ready?
Yep.
Ready?
Don't let it seal.
1,
In order to remove any water from the final product, we added anhydrous sodium sulfate to the organic later. Once it was transferred to a beaker. Here, we swirled the solution until the sodium sulfate can no longer clump together, and instead remained suspended in the solution. As you can see on screen, we added enough until we could see the sodium sulfate no longer clumping. If you see sodium sulfate in the solution swirling around, you may need to perform a gravity filtration before moving to store your product for the next day. Still a sludge. So now we
No! Yay!
Cool. The final step was to purify using distillation. The entire setup included a vacuum portion of the distillation setup in order to ensure that the desired product was reaching the collection flask only. However, due to there being only a few compounds in the initial round bottom flask, we opted to not use it as it likely wasn't necessary. When setting up, make sure that the thermometer is pushed down far enough into the setup to obtain an accurate reading. If the reading is off, the product will not be as pure. We collected in a 25 milliliter round bottom flask. We continued the distillation until there was little to nothing left in the initial flask. Here we see our final product. Smells like banana. Lastly, we moved to analyze our results. We then headed into the analysis portion of the lab, where we had to ensure that the product we obtained was the one we are looking for. First, we cleaned the NMR tubes as you see here, using acetic acid. We then left them to dry, and added our substance plus a small amount of TMS to the tube before adding it to the NMR machine. Once in the NMR machine, we went through the appropriate steps to obtain the integration, to fit it properly to a graph, and to obtain the chemical shift values for each of the peaks. We found that we obtained a 12.19 gram yield out of a theoretical yield of 19.53 grams, resulting in a 62.45% yield. While not exceptionally high, this yield could likely be increased with better technique when undergoing distillation by heating to completion. While the yield was not exceptionally high, we can see by the NMR spectra that the product was especially pure, which would be necessary when synthesizing isopentyl acetate for food production. The atom economy was high as well, with a 0.8785 atom economy and a 54.86 reaction efficiency. This was a fairly green reaction, not utilizing much of anything toxic besides 1 milliliter of sulfuric acid. The total chemical equation you see on screen here represents what went on during the reaction. Here is the mechanism that supports the creation of the final product. In case something went wrong, let's go over a few possibilities for what would change. If water was present during the distillation, the boiling point for the solution would be thrown off and the final product would be contaminated. If sulfuric acid was not added, the reaction would likely take much longer to occur, if even occur at all. Doubling the amount of acetic acid would slow the reflux reaction as it is already in excess. Adding more would only slow it further. If you forgot to use sodium bicarbonate, the final product would likely be contaminated with water and acetic acid. If the thermometer was not pushed down all the way, the temperature for the distillation would be off and the product would not be as pure. Thank you for watching. Your work has greatly helped the Cavendish Distilling Company and even allowed for bananas to be used for food rather than alcohol in the future. Great work.